Hello and welcome to this Eikon Data API tutorial. My name is Yves. I'm founder and managing partner of the Python Quants. Today's tutorial is about deep learning, and in particular we're going to use deep neural networks to do financial time series prediction. Deep neural networks, of course, used already in many different areas as of today, and we might want to see whether there is something in using DNNs for the prediction of financial time series. The agenda is as follows. We first retrieve intraday price data. We then prepare lagged data because the whole analysis will be based on lagged returns data. We implement the DNN model for classification, and we use the results from the predictions of this model for vectorized backtesting. We then move the analysis to a more realistic scenario where we train the model on a part of the data set that we have available and test it on another part to see how the model might perform out of sample. I move to the Jupyter Notebook, and as usual, you find what to expect from this tutorial, and the first code that you find is about imports of important packages, and in particular we're going to use Tensorflow, which has been open sourced by Google and is used in many different areas as our package for deep learning. Quick look at the versions, in particular maybe Tensorflow might be of interest here, and then I connect to the Eikon Data API, which here in this instance requires that the proxy or the application is running in the backend. First step is now to retrieve intraday data for a rather small universe of RIGs, just 3 RIGs that we're going to use here, 1 ETF and 2 stocks. And then we retrieve the data. Wait until it's finished. We now have our data set available. It's for a single day only and for just a few hours. It starts here at 12 p.m. you see, and it then goes by the minute. Having a look at the tail end, we see that it ends exactly at 4 p.m. on this day. We apply TropNA to make sure that we have a complete data set throughout, and as an intermediate step, we also calculate the log returns, which we're going to use later on for the vectorized backtesting. So here we have now the log returns for our 3 RIGs. Let us plot the data. On the one hand, here the normalized intraday evolution of the 3 RIGs considered, 2 stocks and the 1 ETF. And for the same set of RIGs, also here the frequency distributions. So here's the grams of the log returns. Now we're going to prepare lagged data. We use 10 lags in total. So here lags are defined, and this function add lags is a convenience function which you can apply to the different data sets for the different RIGs that we have collected. So here the definition of the number of lags and the function add lags. And via this little loop, we're going to add lags to the original data set that we are interested in, so that we later have the data that we are looking for. So the cols, these are the names of the columns which have the lagged data. You see here, this is lag by 1 time interval. In our case, it's 1 minute bars. It could be 1 day, it could be 5 minute bars, depending on the data we are working with. And here you see the keys of this dictionary. And when we have a look at the head of the Apple related data frame, we see we have the original returns here, and we then have the lag data. But we won't work with the absolute values here. What we're going to do later on is illustrated in the next cell. We are going to derive binary values here, zeros and ones only, and in particular this is 1 here when the return is positive, and it's 0 when the return is negative. This is what the MP digitize function does here, with the bins defined just being a single number 0. The total number of patterns considered here are 2 to the power of lags, and this translates into 1024. Now to the DNN model. And what follows, we're going to use a TensorFlow. And in particular, we will use a deep neural network classifier. And the classifier shall learn from historical patterns to predict whether an upwards movement is more likely or a downwards movement. Before I get started, I set the verbosity to error only. We're only interested to see errors if there are any. And we define the features first. So for every single column, we will have a feature defined here in the dictionary. And what I have done before with digitize, TensorFlow can do with the bucketized columns here. So out of the real valued columns, I'm creating here bucketized columns. The boundaries are set as before, so we just are interested in positive and or negative values at this stage. Now I fit the model. And in order to get this started, I need a function which returns both the feature columns data and the labels data. And this is what getData is supposed to do. So here you see the feature columns are delivered as dictionary, and the labels are here just a single vector, a single tensor, constant here. And we use digitize once again to come up with the zeros and ones that we need for our prediction or the modeling, so to say. Now the DNN can be trained, so to say, fitted to the data, and the neural network and deep learning world, we typically speak of training instead of fitting. And the DNN model object is instantiated with 3 hidden layers. Not a huge thing, but already kind of a flexible deep neural network that we built here. This is done here for every rig anew, otherwise the model would learn with data added to it. So we instantiate for every rig here new model. We pick out the data that is relevant, and we fit the model given the data as delivered by the getData function. We use 250 learning steps, not that many, but hopefully enough to come up with decent results. Then we do the prediction based here just on the in-sample training data set, and we put the results into a column in the respective rig. We translate then the results from zeros and ones to plus ones and minus ones. So this is what we do here. Whenever we have a positive value, a plus one, we leave it at plus one. If we have a 0, this is then translated, as you can see here, to a minus one. So this takes a few seconds when I execute this cell, because it iterates over the 3 rigs. It does the training based on 250 steps per rig. After 10 seconds on my machine, it's finished. And when I have a look, for example, at some results, we see that we now have indeed in the position columns of the respective data frames, we have plus ones and minus ones. And these are now the predictions given the patterns observed in the markets for the last 10 lags. So the 1024 patterns that are distinguished are observed, and depending on what the deep neural network has learned, it forms its prediction, and that it says, well, an upwards movement is more likely after this pattern, or a downwards movement is more likely after that pattern. So here we are using an admittedly small data set only to keep computation times and training times pretty low. In real practice, probably you would work with a larger data set. But let us have a look at how the strategy based on a deep neural network performs. We apply vectorized backtesting here to this end, and we use our positions and multiply positions by the returns, the log returns, and this allows us then to visualize the strategy performance compared in relative terms to the benchmark investment, which would be just a passive long position in the respective rig, here the ETF And you see, in sample, the strategy performs pretty well. So the deep neural network seems to be flexible enough to learn the patterns and their predictive powers there. We can have a look at Apple here as well. The same holds true. Plu significantly outperforms over this short period. The passive benchmark investment, the same holds true again here for the third rig, Amazon. But of course, a couple of things have been completely neglected, like the number of trades, transaction costs, and one major point that I want to address in this notebook is that we just test here the performance in sample. So we train the model based on a given data set, but we don't check how it performs outside of this data set. So I won't introduce transaction costs as one element that would make the analysis more realistic. But I think the most important one that we can do is that we check how such a model trained on some data performs out of sample. So in machine learning or deep learning, you typically speak of a train test split. In finance, sometimes in sample and out of sample. And this is what I stick here with. So we do a half-half split. This is more or less arbitrary. It might come natural, but I think there are other rules that we can follow. We could also think of a random split as one other example, but here we have the half-half. And when I now visualize, this translates into the following. We have the time span that we cover with our data set. In this particular case, it's 4 hours on the single day. We take the first, not exactly 2 hours. You see it here, it's slightly moved. We take the first half of the data rows that we have, and then after we have trained the model on this first half, we take the second half of the data set and test the performance on this data subset. And this is what is implemented here in this cell. So the cell with the loop over the rigs has grown a little bit. And in particular, what is added here is that we do the fitting based on the first part up until the split number. And we do the prediction here from the split value, so on the second half. We then derive the prediction values and we collect now the results in a new results dictionary where we have for every rig a separate data frame that we use. So this is why the cell here is a little bit longer, has more lines of code, and there are also a few more comments in between. I execute this. This should take roughly as much time as before. It's a little bit faster because we train and test on smaller data sets. And we see here now in, for example, the data frame, which is stored under the rig AAPL.O for Apple, we have now from 1414 on the returns of the stock, the prediction value, and we see the strategy now is multiplied by -1, which is the prediction, so we would be short. Same holds true here. So in one case it's correct to do so, here it's incorrect, and so forth. And I can now do the same as before. I can visualize the performance of the strategy out of sample over time. And what we see here is that for the S&P 500, it seems to outperform. The ETF here on the S&P 500 seems to outperform the passive investment. Then we have a case here for Apple where it underperforms. And here it slightly outperforms. So you see, once we move towards out of sample, we can get, so to say, anything. So here by incident, we have 3 different cases: a good performance, which means a positive absolute return, as well as a significant outperformance. Here in this case, we have an underperformance. And the underperformance also leads to a negative result in absolute terms. And we have a negative result where we have a little bit of an outperformance. So I guess even if this is an outperformance, you wouldn't consider this to be a proper success because we would lose money based on the strategy. And this does not even factor in transaction costs or any other market microstructure elements that might apply here in this context. But nevertheless, we have seen in sample, we see good performance, and of course we could now take this as a starting point and try to come up with better modelings, with better features, in this case with better performing parameterization, so for example more training steps, to name just one, or maybe to increase the number of hidden layers in a deep neural network, and so forth. Of course, the flexibility is there and the adjustments are in generally easily made. Which brings me to the conclusions, and based on this tutorial we can conclude that it is easy to retrieve historical intraday data and to get started with data analysis based on the Eikon Data API. Plotly and Cufflinks, like usual, prove valuable companions when it gets to financial data visualization. Deep learning techniques, in particular deep neural networks, seem to be kind of pretty powerful. We have seen this in sample and not in the same way out of sample. But again, a little bit more effort probably should be put in such an analysis. And if there is something in it or not, I think this is open after our analysis of the out of sample results. But at least you have seen that it's kind of straightforward to apply popular, powerful deep learning techniques in our domain to financial price and time series data. And this should be a good starting point for further research on your end. Like usual, towards the end, you find the resources for the Eikon Data API. Feel free to explore these. And I'm up to finish today's tutorial with a final look at the agenda. And for me, it remains to say happy Python coding and also happy deep learning, and see you in the next tutorial.